In this video, we'll discuss the relationship between continuity and differentiability. Now recall, a function is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Okay, so what does that mean? Well, continuity requires three things. First, for it to be continuous at x equals to a, then the function has to exist at a. So that seems pretty obvious, I think, there. Then the next condition is that the limit as x approaches a of f of x exists. Now usually that means we need to make sure that the limit from the left and the limit from the right both equal to the same value. And that, for the third thing, is not only does that limit exist, but that it's equal to the value of the function at a. So putting it together, the first condition. Now a function is continuous on an interval, should be on an interval, if it is continuous at every number in the interval. So like for some examples of where it's not continuous, I'll draw in some, let's see, I draw in an axis. One is called what is called a jump discontinuity. Let's say the function goes, it's like smooth, but then it jumps up to another value. Now, one example of this can occur like in real world applications, like for an electric circuit, that it could jump rapidly from one value to another value. Now, another example of a discontinuity is what is called a removable discontinuity. That means it's like continuous everywhere except at one point, and then it goes on. So, like for this removable discontinuity, we could say at this value a that's equal to some different value. So that the limit from the left and the limit from the right exists and are equal to the same thing, but it's not equal to the same value of the function. The first one was where the limit from the left and the limit from the right did not equal to the same thing. Now another example is what is called an infinite discontinuity. You sometimes see those with rational functions where, let's say, as x approaches some value, let's say like for example, let's just say -2, that as you get closer and closer to -2, the function just keeps getting larger and larger, or maybe from the other direction, let's say it goes down to -infinity. So that's an example of an infinite discontinuity. So that's just a reminder of continuity and discontinuities. Now a function is differentiable at a if f prime of a, which is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h, or another way to state it is the limit as x approaches a of f of x minus f of a over f x minus a, so as long as that limit exists. Now a function is differentiable on an open interval if it is differentiable at every number in the interval. Now, a lot of functions, when we think about it for it to be differentiable, we think about it that it has to be a smooth function. Like, let's say, for example, it's going something like this, like this may be increasing smoothly, or even could be still quickly, but it's still smooth. Now, for an example where it wouldn't be differentiable is if it had like a sharp change. So we're saying that it's not smooth at this point. Now, one of the most common examples of one of these ones where it's not differentiable is the absolute value function, where we often think about the graph as a v. So if you think about it, as you're approaching this value, let's call it a, from the left-hand side, it looks like the derivative is negative, right? Because one way to think about the derivative at a point, it's the slope of the tangent line. So in this case, since this tangent line would be going downwards, that the derivative would be negative. And as we approach from the right, it's going upwards, so the derivative would be positive. But right here, what about at x equals to a? Well, it's jumping from a negative derivative to a positive derivative. So again, this is an example where it's not differentiable because that limit would not exist, because the limit from one side would not equal to the limit from the other side. So what this means is that if a function is differentiable, then we know that it is continuous at a value a. Now this can be proven using the limit definitions, and we're not going to go over this now. It's just trust us that if the function f is differentiable at x equals to a, then f is continuous at a. But this does not go the other way. If f is continuous at a, this does not imply that f is differentiable at a. Again, the most basic example is that absolute value function, because this is a continuous function. It doesn't have is the limit as x approaches a equals to the value of the function at x equals to a, but it does have one of these sharp corners, so it's not differentiable at a. So that's the relationship. So if it's differentiable at a, then it's continuous at a. But it may be that it's continuous a, but not differentiable at a. So it goes one way, but not the other way.